Hi everyone, just answering your feedback from today. Um, did you say that it was worse to break the octet rule or to have a lot of formal charges when assessing different Lewis structures for the best one? For example, could this be the best Lewis structure for get a better marker for N2O? Could this structure be best? Make sure I get this right. Because this structure has no formal charges. A rule of thumb there is that octet rule takes precedence over lowering formal charges in most cases. There will be some times when you'll have elements that can violate the octet rule, and I'm going to talk about some of those exceptions on Friday. But for most elements, for most of the cases that you'll be dealing with, octet rule should always be satisfied, and that should take precedence over formal charges. So yeah, so you can check the formal charges on these. Oxygen here has a formal charge of 0. The nitrogen also has a formal charge of 0. So there's a couple ways you can do this. You can do the box method. Nitrogen normally has 5 valence electrons, and right here it has 1, 2, 3, 4, 5 electrons around it, so it has a net 0 formal charge. And same for this guy, it will have 5 valence electrons normally, and 1, 2, 3, 4, 5 electrons around it. The problem with this structure is that this molecule, or this nitrogen, has only 1, 2, 3, 4, 5, 6 electrons in its valence shell as it's drawn, and so it's violating the octet rule. So this is not the best structure for the simple fact that, yeah, it's violating the octet rule, and nitrogen doesn't violate the octet rule. So in general, first order magnitude, or first criteria to satisfy, yeah, should generally be satisfying the octet rule, unless you have elements that are from the third period and down. So things like sulfur, chlorine, phosphorus, those can all violate the octet rule. The first row, carbon, nitrogen, oxygen, fluorine, they don't violate the octet rule. How do you know where to put the double bonds, single, double? That's not an easy question, or you will rarely not just know where to do it. You may need to do a little experimentation. There is a general strategy, but it won't always be obvious how many or what types of bonds you should be using. So the best way to explain that or to illustrate that is with an example. So let me try illustrating that with the N2O molecule. So N2O, the way you should draw Lewis structures is first determine the number of valence electrons that you need to distribute in your molecule in the Lewis structure. So nitrogen normally has 5. There's 2 nitrogens. So you have 10 plus 6 for the oxygen. So I should try to place 16 electrons in my molecule. Next step is to draw some basic structure for the molecule. And again, even this step can be a little tricky. But this time I think I gave a homework problem about this as well that just asserts that this is the general correct structure, that you have nitrogen in the middle and oxygen around it. So you have a basic structure. Then the third part is to fill up octets. So I've already got some electrons here. This nitrogen already has 2 electrons. So if I fill up its octet, 2, 4, 6, 8, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now everything has an octet. Things are connected correctly. Fourth rule is to go back and check for double and single bonds. And when I say check, I basically mean check the number of electrons in the structure. I'll just say check valence, the number of valence electrons. Because, okay, I've satisfied the octet rule for all of my elements, but if I count how many electrons I've placed in my Lewis structure, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's 20 electrons depicted in this Lewis structure, but I should only have 16 electrons. So this is when you need to start adding double or possibly triple bonds. So I already said that there are 20 electrons here, so I'm going to have to get rid of 4 of them. So I'll get rid of, say, these 4 electrons. Now I have the proper number of electrons, but that central nitrogen doesn't have an octet anymore. So I need to start sharing some of these electrons. Right now, this electron pair is on the nitrogen. It belongs to this nitrogen. But if I share it, that electron pair with this nitrogen, I can start filling up octets. So I have a couple of different strategies. I could use these electrons and share those here, or I can try sharing both of these. I have some options here. I could do this. I could take this electron pair and this electron pair and make a triple bond. This is one possible option. Or I could do something else. I could try taking, not those electrons, but I could try taking these electrons and make a triple bond here. So that's a second option. So I could have or I could do a mixture of these and take one lone pair from this oxygen and one lone pair from that nitrogen and make 2 double bonds. And that would be my third option. And so you may then think, oh crap, I've got a bunch of different options. How do I know which one is correct? That's when you come in with your last step and evaluate the Lewis structures on the basis of formal charges, which is what we did today. And then I think we ended up agreeing that these two were the best because they give you the smallest formal charges. So this guy has a formal charge of 0, +1, and -1. This guy has a formal charge of, what is this, -1, +1, and 0. This one is not so good because it has a formal charge of -2, +1, and +1. So this one has the most formal charges, so it's not really the best possible structure. These two are probably better because they have smaller formal charges. And if you had to choose one, you don't really have to choose one. You could say that there's resonance between these two structures. But if you had to choose one, I would probably choose this one, simply because it puts the negative formal charge on oxygen, and oxygen is more electronegative than nitrogen. This Lewis structure puts the negative charge on nitrogen as opposed to the oxygen. If I was going to put an extra negative charge somewhere, I'd probably put it on oxygen because it's more electronegative. So that's essentially how you know where to put the double bonds. You have to do a little bit of experimentation. So it can be a little tricky, but then the best way to do it is get lots of practice so you get quick at doing it. Do we have to memorize formal charges for each element? No, you don't have to memorize formal charges. That is one strategy for predicting formal charges, is to basically do pattern matching. Like, for instance, I've gotten to the point that if I see an oxygen that looks like this, I have memorized that this is a case where oxygen has a formal charge of 0. If I see a case where oxygen is making 1 bond, this is a case when oxygen has a formal charge of -1. And you'll almost never see this, but if it ever does occur, if I have oxygen making a triple bond like this, that's a case where oxygen has a +1 formal charge. So you can just memorize these patterns, but I wouldn't recommend it. It's faster because your brain is better at just remembering facts usually than actually trying to work out and calculate and analyze things. That can take a little bit more time. This is faster in the heat of the moment, but it takes more groundwork, more preparatory work on your part to memorize all of these. And then you're slightly, I would argue, you're more likely to make mistakes and remember something incorrectly versus here where you have a very basic principle or a basic algorithm to follow where there's just only one thing to memorize and then apply it. So I would say you don't have to memorize them. You may end up memorizing them on accident just by doing it many, many times, but you can memorize them if you like. Is bond length inversely proportional to bond energy? Yes, generally speaking. So the question is bond energy, bond inversely proportional to bond energy? Generally, yes. If you have a really, really strong bond, a bond that's very, very hard to break, that means that the atoms are very much tied together, or very much closely attached to each other, or strongly attached to each other, and that generally corresponds with a short bond. Generally, there are going to be exceptions to that, where you can have a bond that is a little bit stronger, harder to break, but just maybe due to the size of the atoms themselves, it ends up being a large bond. And conversely, you can have short bonds that are weaker than longer bonds, but that is a general trend that a short bond tends to be a stronger bond. Okay, those were the only feedback questions for today. I'm working on the study guide for the midterm, so I'll hopefully try to post that later tonight. I've requested a room for a study session on Sunday. I will email out the information about when and where it will be located once I get the room confirmed. But other than that, thank you for your feedback, and I will see everybody on Friday.